Okay, well, it's a pleasure to have Professor Jonathan Rosenberg from University of Maryland to talk today. And well, you have the floor. Go for it.
Okay, thank you so much.
Thank you very much.
I'll just say by way of explanation for this sort of bizarre way of presenting a seminar, I was supposed to have dental surgery this morning, which I did have, and it went fine, but I wasn't sure if I was going to be able to talk. So to be on the safe side, I pre-recorded the lecture. So I thought, since I have that video ready to go, what I would do is I'd play the video, but I can stop it at any time, and I can answer questions, and I can add to it, and so, et cetera. Okay. So let's see if you can see this. Thank you very much for this opportunity to speak. So the title is about gap labeling and the noncommutative Bloch theorem. And what I'm going to talk about is joint work with Eric Akkermans and Yaroslav Don, who are solid-state physicists at the Technion.
Sorry for interrupting. I don't know if it's just for me, but there is a huge black square on the screen covering part of the slide. Was it just on my end, or?
Same here too.
Same there.
Oh, hold on a second. Oh, let's see. All right, let me stop this and let's see if I can redo it here. Is that a little better?
So there is this big square, this black square with some diagonal white lines that were not there. It wasn't showing this when you first shared the screen before. I don't know why it's showing now.
Let's see if.
And the archive number for our paper is
so, yeah, no, the same thing.
715.
See what this is. No, I don't think I want that.
When you click share screen, are you just like sharing your screen, or are you sharing the like application?
I'm sharing the application.
Okay.
Maybe changing to share the screen to see if it's better.
Let's see. All right, let's.
Yeah, now there's no square for me at least.
Okay, all right, let's.
961. So let me start by talking about the physics background that sort of explains why one might be interested in this. And the first topic that comes up, even though it's not in the title, is the subject of quasi-crystals. So first of all, what is a quasi-crystal? I think most of you are familiar with crystals. Most solid materials are built out of crystals, for example, or at least metals are. I mean, not things like wood and plastic and so on, but metals are built out of crystals, which involve regular arrangements of atoms in a lattice. And quasicrystals are not quite crystals, but they have some of the same features. And they were first discovered by Dan Schechtman and his collaborators. And here's one of his Schechtman's very earliest papers on this subject. So this is from, I think, Metallurgical Transactions from 1984. Yeah, 1984. And it's about the microstructure of a rapidly solidified alloy of aluminum and manganese. So this is sort of typical subject that, metallurgists study. And they discovered the following amazing thing. So they concocted this alloy, and they took X-ray diffraction pictures of it. And here are some X-ray diffraction pictures. Let's see if I can get you a good one here. Okay, so here are some X-ray diffraction pictures, and they look very much like the pictures that you get from regular crystals. On the other hand, if you look at these things carefully over here, you'll see that this can't be a crystal because the kind of symmetry is wrong. I mean, notice how many points you have here in this arrangement. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These points here arranged at the vertices of a regular tengon, and there's no crystallographic group in 2 or 3 dimensions that gives you this kind of symmetry. So it can't be a real crystal. It's got to be something else. And they puzzled over what this would be. Schechtman eventually got the Nobel Prize for this discovery, which was quite remarkable. And so these things are eventually called quasicrystals. And nowadays, we sort of explain them as being, here we are, arrangements of atoms not in a regular periodic pattern, like a crystal, but in a quasi-periodic pattern. In other words, a pattern, for example, given by a non-periodic tiling. Now, most of you have probably heard of non-periodic tilings. One of the most famous of these is the Penrose tiling. Let me see if I can find a picture of it for you. So here's a picture of the Penrose tiling. And you see it's built out of these little polygonal tiles. And at first sight, it looks periodic. But if you look carefully, you see it has a 5-fold symmetry. And there are no crystallographic groups in 2 dimensions with 5-fold symmetry, as we just mentioned. So this thing is not periodic. If you look at it carefully, you'll see that it's quasi-periodic in the sense that there's certain little arrangements that repeat. For example, here's an arrangement like this. You see this pattern is the same as that pattern. So there's certain sub-patterns that repeat, but the whole pattern is non-periodic. So something like that is called a quasicrystal. And so quasicrystals, as they occur in nature, as discovered by Schechtman and people like that, are really examples of non-periodic tilings in the real world. I mean, another way to get a non-periodic tiling, of course, is simply to tie your bathroom with regular tiles, but to arrange them in a funny way. So, if you have rectangular tiles of different sizes and you alternate big, small, big, small, big, small, that's a periodic pattern. But if you do big, small, 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 big, small, big, big, small, something like that, you can get something that looks like a quasicrystal. All right, so that's sort of background on what quasicrystals are. Now, the other word that appears in the title here is the Bloch theorem, so I should explain what that is. So this is something that's familiar to solid-state physicists, but it's probably not familiar to mathematicians. And it's just the statement that in a crystalline solid, eigenstates of the Schrodinger equation are given by plane waves modulated by a periodic function. So basically, that's because the Schrodinger equation for a crystal involves a potential which is periodic, and that potential function, oscillates up and down along with the variations in the crystalline lattice. Now, the question is, what replaces Bloch's theorem in a quasicrystal? You now have a potential which is not periodic anymore. Instead, it's what you can call quasi-periodic. It's not quite exactly the same as the notion of quasi-periodicity, let's say in the sense of Wiener or something like that, but it's very similar. And so we want to understand what is the replacement for Bloch's theorem in a quasicrystal. And the first person to really study this in an intensive way was Jean Bellissard, and he and his collaborators have been working on this for about close to 40 years now. Okay, so I'm not claiming tremendous originality for everything that's going to be in this talk. A lot of this is just going to be a kind of review of work that's been done by a lot of different people, but there will be a few new results toward the end. But anyway, this is a kind of a mixture of a kind of a survey talk and a few new results. And I'm not going to give complete attributions for everything because that would take forever, because there are literally dozens of people who have been working on this subject, and various people put in tiny little pieces of the puzzle, and it's very complicated to try to give an accurate history of who did what in what order and that sort of thing. So I apologize in advance to the people whose work is maybe being slighted here, but I'll mention a few of the major contributors. Bellissard is certainly one of the most important. Okay, so let's start by talking about tiling spaces, since we're talking about non-periodic tilings. So consider a tiling of RD by finitely many shapes of tiles. And tiles that are translations of each other are considered to have this same shape, but we don't consider tiles that are rotations of each other to be identical. Okay, so going back to this picture over here, the Penrose tiling, here you see these triangles can occur in various orientations. And so each time the triangle occurs in a different orientation, we count it as a different kind of tile. There's still only finitely many tiles in this picture. So if the orientation is the same, so like this triangle here and this triangle, we count these as being identical. If the orientation is different, like this triangle and that one, then we count them as being two different kinds of tiles. But there's still only finitely many kinds of tiles. It doesn't really matter. Okay, and now there are certain other sort of basic axioms for these tiling spaces. We assume each tile is a polyhedron, and the tiles meet full face on full face. Okay, so over here you see this, for example, is a triangle with three faces. This face joins exactly to the face of another triangle, and so on. All right, this is a reminder to me just to show you the picture of the Penrose tile. We just did that. So now take the set of all, whoops, this should be tiles, not times. Take the set of all tiles and consider the set of all tilings that can be formed by the tiles in P. So R to the D acts on this by translation, because you can take the whole picture here and just slide it left and right, up and down. Okay, so you get a space X, which is called the tiling space, and under one other assumption, which I forgot to mention, which is finite local complexity. So finite local complexity means that inside any ball of radius r in this picture, there are only finitely many kinds of configurations that can occur. That's due basically to the fact that we have finitely many tiles and they can only be arranged in certain combinations, all right? So when you have finite local complexity and all these other axioms, then this tiling space X is compact. And in the case of periodic tiling by D cubes, so for example, like just a square lattice in the plane, then X is just going to be a torus. It'll be R to the D, which is acting transitively now on X in this case, divided out by Z to the D, because if you translate by one square of the lattice, you just come back to exactly the same pattern again. All right. So a tiling, anytime you have a tiling with finite local complexity and these other axioms, you get a tiling space X, which is in a compact space with an R to the D action. And a famous theorem of Sadoun and Williams says that X is topologically a fiber bundle over a torus with a fiber that is compact and totally disconnected. So in the case of a periodic tiling, that's the one associated with one of the familiar crystallographic groups, then the N is just a finite set. And then this X, in other words, is just a finite covering of a torus. But if you have a quasi-periodic tiling, like Penrose tiling, for example, then this N will be a Cantor set, and the X will be basically a fibration of a Cantor set over a torus. And you have this R to the D action on it. And of course, the R to the D action on the, well, this homeomorphism between X and this fiber bundle is not necessarily equivariant for the R to the D action on the original tiling space. But if you change the tiling space, then you get an almost equivalent tiling space where the action is just translation. So in other words, the action of R to the D on X pushes down just to the transitive action of R to the D on the torus. And in general, even though the homeomorphism between X of P and this fiber bundle is not necessarily equivariant, it's always an orbit equivalence. In other words, it sends orbits to orbits. It just may not exactly match up the R to the D actions. So that's good enough for our purposes, because for what we're going to talk about, orbit equivalence is enough. So you can assume that your tiling space just looks like a fiber product like this. You have a compact, totally disconnected space N with a Z to the D action on it. And then you take the fiber product of R to the D over Z to the D with N. And that will give you a fibration that looks like this. And this X will be what's called a foliated space. So it's not a foliated manifold because this isn't a manifold. Remember, the N in general is Cantor set. So the topology of X is not as nice as it is in a manifold, but the leaves of the foliation are indeed manifolds. They just look like copies of R to the D or things covered by R to the D. And since you have this R to the D action on X, we're assuming X is equal to this, then you get a cross product C-star algebra, C-star of X cross product by R to the D, and by sort of basic results of Rieffel and Green, this cross product is Moridi equivalent to the one that you'd get just by taking the Cantor set N and acting on it by Z to the D. So for most C-star algebraic purposes, and you'll see what the C-star algebraic purposes are in a moment, you can replace this non-unital C-star algebra by this unital one over here. C of n cross product by z to the d. So now here's the basic operator theoretic problem. This is an operator theory seminar after all. So how are we supposed to understand the diffraction spectrum and the Schrodinger operator spectrum of a quasicrystal using all of this setup? So, you know, when you have a quasicrystal, if you shoot X-rays through it, you get a diffraction spectrum that involves a kind of operator theoretic problem to compute that. And there's also, if you want to measure material properties of the quasicrystal, like the, you know, heat conductance, the magnetization, things like that, those all have to do with the Schrodinger equation. And the Schrodinger equation, as we said, has this quasi-periodic potential on it. So how are you supposed to compute facts about the spectrum of the Schrodinger operator using all of this setup? So that's the basic operator theoretic problem that I want to talk about. So it turns out that even though the basic problem and, you know, is really one of operator theory, it really comes down to a lot of questions that involve topology, geometry, and operator algebras. In particular, this tiling C-star algebra is going to play a very important role. Okay, so let's. Now we're hereafter going to assume X is of this type, so it's part of the D crossover Z to the D with N, where N is totally disconnected. So this thing, of course, fibers over T to the D in an obvious way. If you were to collapse N to a point, that would send X to T to the D equivariantly for the R to the D action. And this X is a foliated space with the leaves of the foliation coming from the R to the D action. And let's assume that the holonomic cover of each leaf is R to the D itself. That's automatic if the action is free. I mean, this is a rather minor technical assumption. I don't want to explain what happens if you violate that, but it's not so important. So then this tiling C-star algebra that we talked about is basically the same as Kahn's foliation C-star algebra in the foliation index theorem. This is the basic idea of Bellissard, and that is that the Schrodinger operators on the quasicrystal look like self-adjoint elements of this C-star algebra. Now, that's not exactly literally true, because the Schrodinger operator is unbounded. But if you take, apply spectral calculus to it to cut it down to a bounded operator, the kind of bounded operator that occurs is an element of the C-star algebra. And now, one of the most important problems.
Just one thing, I don't know if I missed it. What is G?
Solid material, and you know what it's.
Sorry, what?
Sorry, I don't know if I missed it, if you mentioned before or not, but what is G?
Oh, G is the groupoid, which is just, if you like, Z to the D acting on N. Okay, or R to the D acting on X. Sorry, so this C-star algebra is a C-star algebra of a certain groupoid. It's the action groupoid for the action of R to the D or Z to the D on the either on the Cantor set or the whole tiling space X. Okay, yeah.
Schrodinger operator is to try to determine where the gaps are in the spectrum, because the gaps in the spectrum of the Schrodinger operator determine lots of the chemical and physical properties, like whether the material is a conductor or insulator, the specific heat, all sorts of things like that. So all those are related to the gaps in the spectrum of the Schrodinger operator. So since the Schrodinger operator looks like elements of the C-star algebra, self-adjoint elements of the C-star algebra. The spectral projections of the Schrodinger operator are projections in the C-star algebra. This C-star algebra is non-unital. If you want, you can replace it by this unital one over here. Anyway, so the spectral projections of the Schrodinger operator look like projections in the C-star algebra. So if you know something about how many projections there are in the C-star algebra, then that gives you information about the spectrum.
Oh, let me just pause here and explain something. So I think those people who work in C-star algebras probably already know this, but we're about to introduce the K0 group of the C-star algebra, and by definition, that's just the Grothendieck group of the set of projections in the C-star algebra. So it just consists of formal differences of projections, and so if you want to know how many projections there are in the C-star algebra, then the obvious thing to do is to look at this K0 group.
On the other hand, there's also the diffraction spectrum, which is computed a different way. Basically, that involves plopping down an atom at each point of the quasi-crystal and then taking the Fourier transform. So, and you can study what that tends to look like. And it turns out the diffraction spectrum is closely related to the Čech cohomology of the tiling space. I won't explain how that connection comes about, but because that's a kind of a long story, but you can take my word for that. So all right, so now what do we have? We have the C-star algebra and its K-theory, and we have the cohomology of the tiling space. Now, when you make a physical measurement on a physical system, so let's say you have this this quasi-crystal and you make a physical measurement of it, then what you're actually going to measure is going to be some numbers, and those numbers come from converting these abstract groups. So this is an abstract group, this is an abstract group. So what you measure is not an abstract group, but you measure the image of this abstract group in the real numbers under some map, and that map turns out to be the trace that comes from some invariant transverse measure on the foliation. Now, I should mention there's one more topological
again and just
invariant
explain another thing. So this trace in the let's say case of the Schrodinger operator means that basically we are you want to compute not just how many spectral projections there are, but how big they are, right? So the actual values of the, the sizes of the spectral projections are given by a trace, and that trace comes from integrating against the transversal, which is this Cantor set with respect to a certain invariant measure. And that's this invariant transverse measure that's going to show up over here. In the quantity that comes out in physics terminology, I think is sometimes called the integrated density of states or something like that. But anyway, it's basically a trace applied to that projection. In the literature, this is called the tangential cohomology. And it also goes under the name of tiling cohomology. And this is the cohomology, this should be cohomology, not homology here. That's the cohomology of the tangential de Rham complex along the leaves of the foliation. And that has a natural topology, but it's not always Hausdorff, as it turns out. And so here are some of our results. So now we'll finally get to some
new fact. So first of all, if you compute the Čech cohomology of X, so this is the Čech cohomology of the tiling space, it's the same thing as the group cohomology of z to the d, the lattice, acting on the cohomology of the zero-dimensional space n. So n, remember, is totally disconnected. It only has cohomology in dimension 0. It's something like a Cantor set. So this is a countable free abelian group. Z to the d acts on there. The action comes from the action of z to the d on n. And then the cohomology of this group acting on that free abelian group turns out to be the cohomology of X. We're particularly interested in the top degree cohomology. So X is d-dimensional. Remember, it's a Cantor space fibration over a torus. And the top degree cohomology of X turns out to be the co-invariance of the action of z to the d on H0. So covariance means that you take this this group over here and you divide out by all things of the form gx minus x, where g is an element of the group acting on some element x in the abelian group. Now, if you're interested in the real cohomology of X, that's just the same thing as the cohomology of z to the d acting not on H0 with coefficients in z, but instead the C infinity functions on n. So when you have a totally disconnected space, a C infinity function by definition is a locally constant function. So these are the locally constant functions on n. And the cohomology of z to the d acting on the space of locally constant functions gives you the cohomology of X. The tangential cohomology, on the other hand, which we mentioned before, is the cohomology of z to the d acting on all continuous functions. So notice there's a natural inclusion of the locally constant functions into all continuous functions. So there's a natural map from this into this. And that map has dense image because the C infinity functions are dense in all continuous functions. And in the uniquely ergodic case, that's the case where there's a unique invariant transverse measure, then the Čech cohomology surjects onto the Hausdorff quotient of the tangential cohomology. And in that case, the Hausdorff quotient of the tangential cohomology will be one-dimensional. So now, for everything that follows, we just fix an invariant transverse measure mu. And then you get something called a cohomology trace and also a K-theory trace. So the cohomology trace is a map from the Čech cohomology of X, which remember is H upper 0 of n z to the d coinvariance. So it's a quotient group of H upper 0. So that thing maps to R, and this map here is induced by the transverse measure, because the transverse measure, of course, is a measure on n on this Cantor set. And if you have an element of H upper 0, that corresponds to a well, this group here is spanned by characteristic functions of Clopin sets. So if you have a Clopin set in n, you can just take its measure and that gives you a map to R. So that's called the cohomology trace. On the other hand, there's also something called the K-theory trace, and you get that as follows.
you take this cross.
So I should pause here for a second. So actually, what I should have said is that the K-theory trace, the invariant transverse measure defines a trace on that tiling C-star algebra. And the K-theory trace is just the map. Anytime you have a C-star algebra with a trace on it, you always get an associated map from K0 to the reals. And that's the K-theory trace. But then it turns out that it can also be computed in this other way.
Product, this is the tiling C-star algebra. Take its K-theory. So K-theory, remember, records the how many classes of projections you have in this algebra. And the projections here are relevant for the Bloch theorem because the spectral projections of the Schrödinger operator are expected to be projections in the C-star algebra. So you have a map from K0 of the C-star algebra, which is generated by the projections, that goes to K to the minus D of X. These things turn out to be isomorphic to each other because of Kahn's tome isomorphism theorem. And then you can apply the partial Chern character. So this is the part of the Chern character in top degree that goes from KD of X to HD of X, and then compose with the cohomology trace. And this composite turns out to agree with the map from K0 of the C-star algebra to R that's just induced by the trace on the C-star algebra attached to the transverse measure. So if you're given this transverse measure mu, it defines a trace on the C-star algebra. If you have a projection in the C-star algebra, you just apply the trace to it, and that gives you a number. And this map over here is the K-theory trace, and that turns out to agree with this composite over here. So this was the gap labeling conjecture. Right. I was kind of unsure how to spell this here because some people spell labeling with one L and some people spell it with two. Turns out if you look in the dictionary, they're both correct, so I'm not sure what's better. But anyway, let's say we spell it with one L. So the gap labeling conjecture, which is due to Bellissard, is that the image of the K-theory trace, which is on the K-theory of this big C-star algebra, it actually coincides with its image on the smaller subalgebra, which is just C of X. Notice C of X is sitting inside this whole thing here. And so if you take K0 of C of X, that's sitting inside K0 of the cross product, so to speak. And the rather surprising conjecture is that the K-theory trace on this big algebra just agrees with what it is on the smaller algebra. That means somehow or other, adding all this non-commutativity doesn't really add anything to the problem. And that's a little bit surprising, but it seemed to be borne out in a few basic cases that Bellissard tested, and so he made this conjecture. Now, this thing called the gap labeling conjecture morphed into something called the gap labeling theorem. There were three groups of people. Here they are. Moulet Ben Amour and Hervé Oyano and Kamaker and Putnam and Bellissard, Benedetti, and Gamboto. So all three of these groups, right around exactly the same time, 2003, claimed to prove this conjecture, the gap labeling conjecture. And the papers were written and published independently, but they got a joint featured review in MathSciNet that advertised the fact that this major conjecture had been resolved. So back in 2003, people thought that the gap labeling conjecture was actually the gap labeling theorem and that three different groups of people had proved it. There's just one problem, and that is that all three proofs were wrong, and they were all wrong for basically exactly the same reason. So we'll come back to that in a little while. But
So it took several years for people to realize the mistake. But anyway, now I think it's more or less agreed by all the people involved. I mean, I've talked personally to Ben and Moore, to Kamaker, to Putnam and Bellissard, all, and so I've talked to most of the people on this list, and they all agree that the proofs were wrong, and everybody agrees as to what the mistake was. So I'll tell you what the mistake was at some point, and we'll see what the correct statement is. So here's our theorem 3. So theorem 3 says that this diagram over here. So over here, this is the K-theory trace from the K-theory of the tiling C-star algebra to the reals. Over here, you have the cohomology trace from the Czech cohomology of X to R. Both of these are induced by the invariant transverse measure. So this transverse measure, as we said, gives you a way to measure the size of clopin sets in X. So that immediately gives you a map over here. Whereas, well, not clopin sets in X, they're clopin sets in N. But remember, the Deith cohomology of X turned out to be the coinvariance of the zeroth cohomology of N, where N was the totally disconnected space. So it's and N is the transversal basically to the orbits. So a transverse measure is really not so much a measure on X as a measure on N. It's a measure on the transversal, which is invariant under the z to the d action. So that gives you a map from the coinvariance of z to the d on H0 of N to R. That's the cohomology trace. And this diagram turns out to commute, and the K-theory trace sort of goes through. This thing over here is Kahn's tome isomorphism, and this is the top degree component of the Chern character. So checking that this diagram commutes is not a trivial thing, because the way the K-theory trace was defined didn't seem to have anything to do with the Chern character. So, to prove this equality, you really need to use something like the foliation index theorem. And so this formula with the Chern character in it basically comes out of the foliation index theorem. So, so that diagram commutes, and then the gap labeling conjecture is equivalent to the Chern character of k the d of x, k the minus d of x, and the Chern character, and and the integral part of the cohomology having the same image under the cohomology trace. Now, here's the problem, and this is basically why all the proofs were wrong. That is that the formula for the Chern character, which goes from K-theory to cohomology, has denominators in it. So for most spaces, it goes from the K-theory not to the integral cohomology, but to the rational cohomology because of these denominators. The denominators come from the factorials that occur in the series expansion of the exponential function. So in general, for general space, the Chern character of the K-theory does not end up in the integral cohomology. Now, there are a few spaces for which it happens that it does end up in the integral cohomology. For example, it's a classical theorem that for a sphere, the Chern character of a sphere ends up in the integral cohomology, but that's rather exceptional. For other spaces, like, for example, complex projective spaces, that's not true at all. All right, so in general, the Chern character does not end up in integral cohomology, so there's no reason why the image of the Chern character should coincide with the integral cohomology. Usually,
it ends up in some part of the rational cohomology, which is commensurable to this, but these groups are usually not the same. However, you can prove that they do coincide for d less than or equal to 3. So for d less than or equal to 3, it follows that the gap labeling conjecture is true. That was noticed earlier by Bellissard and collaborators, although they had a kind of more complicated proof, but this is basically what it comes down to. What's true in general for large D is that if you take the image of the Chern character, which, as I said, has denominators in it that come from factorials, and you multiply by the ceiling function of d over 2 factorial. So this is either d over 2 or d plus 1 over 2, whichever is integral. And then take the factorial of that and multiply the Chern character by that. Then that lands in the integral cohomology. And so the gap labeling conjecture is not off by all that much. It's basically off by this factor, or so it would seem. Now we actually, to be honest, nobody has found an example of a tiling space where the Chern character does not end up in integral cohomology. I have a kind of a idea as to how to construct a counterexample, so I really do believe that this is false in high dimension. The earliest dimension for which it could be false would be in dimension 4. So I wouldn't be surprised if, in general, this does not end up in there, and therefore the gap labeling conjecture is false in dimension 4 and up. But since real world quasicrystals always have dimensions 1, 2, or 3, for the physical applications, maybe that's not so important. So I actually don't know of any physical applications of 4-dimensional quasicrystals, although I wouldn't be surprised if somebody comes up with some. But right now, that's a kind of an open problem. But the problem of finding a counterexample is still open. All fraction spectrum versus the Schrödinger spectrum. That's been analyzed in detail and has been tested experimentally for d equal 1. You can form one-dimensional quasicrystals in the lab and measure their properties. And it turns out the diffraction spectrum can have what are called Bragg peaks. So these are these sharp dot patterns that you see over here. Or Lebesgue spectrum or a singular continuous spectrum, any of those, which in this picture would just sort of show up as a kind of a gray fuzz. Experiments show that the Bragg peaks match up well with what's predicted by the cstar algebraic gap labeling conjecture, or in this case, it's actually a theorem because we're in d equal 1. So for those one-dimensional tiling spaces, it turns out that the program actually does relate these various kinds of spectra very nicely to the K-theory of the cstar algebra and to the Czech cohomology, and all of them give the same answer. Okay, so
that's that was all for the video, but I guess that was exactly 50 minutes. So it's so I can stop here and happy to answer any questions. And
okay, well, let's thank Professor Rosenberg. Are there any questions? I see Ben unmuted himself. I don't know. Okay, never mind. So I have a question actually just on the historical
Sure.
part of it. So how
Yes.
how were those three results found to be not that the result is false, but that the proof was wrong? Was it recent? Does it have anything to do with this current paper of yours, or?
No. The mistakes were discovered earlier. Actually, this whole subject has a history of many mistakes. So another mistake that was made was that at one point somebody claimed to have proven that the Čech cohomology of a tiling space never has any torsion in it. And that turned out to be just blatantly false. It was just basically a wrong calculation. So these calculations are kind of tricky, and it's easy to make mistakes in them. And so that was an example of another mistake that came up. And this was due to a similar kind of thing that people thought they had proved that the Chern character always has to take integral values, and just didn't, I mean, proof just didn't make any sense. So.
Okay. Oh, sorry. Ben is saying something here. What is it? Oh, never mind. Sorry. Sorry, I just saw some old message here in the chat, and I thought it was something new.
Okay.
So any other questions to Professor Rosenberg?
Well, I'll just mention another interesting operator theoretic problem, which is to try to determine when you have these Bragg peaks. So that's sort of related to having a point spectrum for the operator that's associated with the X-ray diffraction. And there is some literature on that. And there are some results that say that in some cases you do get Bragg peaks, in other cases you don't. And basically, as I said, when you have Bragg peaks, then you expect to see an X-ray diffraction picture that sort of looks like the one from a crystal. And when you don't, then you wouldn't see that, and it wouldn't seem as crystal-like. But that hasn't been totally resolved in all cases. It's just known in a few cases where there are detailed results. But for the one-dimensional case is pretty well understood now.
Okay, if there are no other questions, I will stop the recording. Okay, so let me just stop the recording.